Welcome, everyone. So, in our journey through business mathematics, we often run into tools that aren't just theoretical ideas, but are things used every single day in boardrooms and financial institutions all over the world. Today, we're going to delve into one of the most crucial of these, the present value of an annuity. Honestly, mastering this concept is a huge step in your development as a financial professional. It moves you from just doing simple arithmetic to really thinking strategically about finance. This isn't just about passing an exam, it's about gaining the ability to value a business, or structure a loan, or even plan a corporate pension fund. It's really about understanding the language of value, and that conversation always begins with understanding the dimension of time.
So, let's start our analysis with a question that seems pretty simple on the surface. Is a guaranteed stream of $10,000 a year for 5 years the same thing as having a lump sum of $50,000 in your bank account right now, today? I mean, the nominal value, the face value of the cash, it's identical. But as financial managers, we have to look beyond the nominal. We have to consider things like inflation, which, eats away at the purchasing power of future money. And more importantly, we have to think about opportunity cost. What could you do with that $50,000 today that you can't do with just a promise of future payments? By the end of our lecture, you'll not only understand that these are fundamentally different, but you'll have the exact mathematical tools to quantify that difference down to the dollar.
Okay, so before we even get into the mechanics of the formula, we first have to really internalize the principle that gives it all its meaning. This is the axiom that pretty much all of modern finance is built on, the time value of money. So let's really explore this core concept.
A dollar today is worth more than a dollar tomorrow. I want you to commit this to memory. It is the absolute cornerstone of financial logic. The main reason, as we've touched on, is opportunity cost. A dollar you get today can be put to work immediately. You can invest it in government bonds for a safe return, or in the stock market for a potentially higher return, or you could reinvest it into a business to fund a new project. That dollar starts working for you, right now. A dollar that's promised a year from now, it has zero potential for this entire year. But there's a second equally important factor here: risk. A promise of a future payment is, well, it's just that, a promise. The company promising it could default. The economy could change. There's an inherent uncertainty in the future that just doesn't exist with cash in your hand. So to compensate for both that lost opportunity and the risk you're taking, we have to discount the value of that future dollar. And discounting is the mechanism we use to translate future value into present value.
So how do we actually do this discounting, not just for a single payment in the future, but for a whole series of equal periodic payments? Well, that's where this formula comes in. I like to think of it as our financial time machine. This tool is specifically designed for a type of cash flow structure we call an annuity, which is just a finite series of equal successive payments. It could be a car loan, a mortgage, structured settlement payouts. This formula lets us take that entire stream of future cash flows and figure out its equivalent lump sum value today.
Now, I know at first glance, this formula can look a little intimidating, but I want to assure you, it is not just some random collection of symbols. It is a precise and logical statement. Each variable you see here plays a very distinct role in the process of discounting. Our goal here isn't just rote memorization. It's a deep understanding of what each of these components represents and how they all interact with each other. So let's deconstruct it piece by piece.
We'll start with N, which stands for the present value of the annuity. This is the variable we're trying to solve for. It's our objective. It represents the single lump sum amount of money today that is financially equivalent to that entire stream of future payments. Now, why is this so vital? It's because business decisions are made in the present. If a project requires a $1 million investment today, we absolutely need to know if the present value of its future earnings is more than that $1 million cost. N gives us that critical comparable number.
Next up, we have R, which represents the recurring periodic payment. This is the fixed cash amount that defines the annuity. It could be the monthly rent you get from a property, the quarterly dividend a company pays out, or the annual contribution to a retirement fund. The critical thing to remember about R in this formula is that it has to be constant for each period. If the payments were all different amounts, we'd have to use a different valuation method. We'd have to discount each payment one by one.
And now we get to I, the interest rate per period. I want you to really spend a moment focusing on this one, because this is the most powerful and often the most debated variable in the whole equation. While we call it the interest rate, in a corporate finance setting, it's more accurate to call it our discount rate or our required rate of return. This rate isn't just some number you pull out of thin air. It's a measure of opportunity cost and risk. It's usually determined by what a company could earn on a different investment with a similar amount of risk.
A higher I means there's either more risk involved in getting the payments or there are better investment opportunities elsewhere. And because of that, a higher discount rate will always lead to a lower present value because we're discounting those future cash flows more aggressively.
And finally, we have N, the total number of payment periods. This just defines the lifespan of the annuity. Now, it is absolutely critical, and I mean critical, to remember that the time unit for N must match the time unit for I. If R is a monthly payment, then N has to be the total number of months, and I has to be the monthly interest rate. Failing to line these up is one of the most common mistakes in financial calculation, and it will give you a wildly incorrect valuation. We're going to come back to this point when we talk about common pitfalls.
You know, mathematics demands precision, and this formula is no exception. The order of operations isn't a suggestion, it is a strict requirement. You have to follow these steps exactly. Let's look at that component inside the brackets. 1 minus 1 plus I inverse n divided by I. This whole expression has a name. It's called the present value interest factor for an annuity, or PVIFA for short. Conceptually, you can think of the PVIFA as a multiplier. For any given interest rate and number of periods, it tells you what a stream of $1 payments is worth today. So once you calculate this factor, you just multiply it by your actual payment, R, to get the total present value. All right, now that we've taken the formula apart, let's move from theory to practice. How is this tool actually used in a business context? This is where the abstract ideas we've been talking about become concrete decision-making instruments. This is how we take our knowledge from the classroom to the boardroom.
The applications are they're everywhere. In capital budgeting, if a company is thinking about building a new factory, they'll forecast the annual profits that factory will generate and discount them all back to present value to see if it justifies the massive upfront construction cost. In mergers and acquisitions, a firm looking to buy another company will use this to value the target's future earnings stream. That becomes the basis for their offer price. And in finance, when a bank gives you a loan, they're basically buying an annuity from you, your stream of future loan payments. The loan amount they give you today, that's the present value of all those future payments calculated using their required interest rate.
To really solidify our understanding, let's walk through a practical scenario. Imagine we are junior analysts at an investment firm. We've been tasked with evaluating a potential acquisition. The target is a small, stable business, and the seller has given us a projection of its future cash flows. Our job is to use the present value formula to figure out a fair valuation from our firm's point of view.
So here's the data we have. The business we're looking at is projected to generate a stable cash flow of $50,000 a year for the next 5 years. So R is $50,000 and N is 5. Now, after our senior partners have analyzed the risk profile of this business and consider our firm's other investment options, they've determined that we need a 7% annual return on an investment like this. This sets our discount rate I at 7%, or 0.07. With these three variables, we now have everything we need to solve for the fourth, the present value.
This slide gives us a really important visual of what we're doing. We are not valuing a single payment. We are valuing a stream of 5 distinct payments. The $50,000 we expect to get in year 1 is worth more than the $50,000 in year 2, which is worth more than the one in year 3, and so on. The payment in year 5 is the least valuable in today's terms because we have to wait the longest to get it. The annuity formula is essentially a powerful shortcut. It saves us the trouble of having to calculate the present value of each of those 5 payments separately and then add them all up. It does the whole thing in one efficient step.
Okay, so let's run the numbers. N equals $50,000 times 1 minus 1.07 to the negative 5 power, all of that divided by 0.07. First, we calculate 1.07 minus 5, which is about 0.713. Then we subtract that from 1, which gives us 0.287. We divide that by 0.07 to get our PVIFA factor, which comes out to about 4.1002. And finally, we multiply this factor by our $50,000 payment. The result is a present value of $205,010. I want you to notice the huge difference here. The nominal value of the cash flows is $250,000, but its actual economic value to us today, given our 7% required return, is almost $45,000 less.
So this is it. This is the moment of truth, where our calculation drives a real business decision. Let's say the seller is asking for $220,000 for the business. As analysts, our recommendation would be crystal clear. We would say something like this. The present value of the business's projected 5-year cash flows, when we discount it at our firm's required rate of return of 7%, is $205,010. The seller's asking price of $220,000 is about $15,000 higher than our calculated intrinsic value. Therefore, if we proceed at this price, it would result in a negative net present value and fail to meet our investment criteria. We recommend entering negotiations with a maximum offer of $205,010 or declining the acquisition. You see, this is how financial math removes emotion and gives us an objective foundation for making strategic choices.
Now, becoming truly proficient with this tool requires more than just knowing how to use it correctly. It also means being aware of the common ways it can be used incorrectly. In an academic setting, a mistake might cost you a few points on an exam. In a professional setting, a calculation error could cost a company millions of dollars. So let's talk about the most frequent pitfalls to make sure you avoid.
Let's really look at these potential errors. First, and by far the most common, is the unit mismatch. A classic example is a 30-year mortgage with a 6% annual interest rate. Students are often tempted to plug in n equals 30 and I equals 0.06. That is completely wrong. The payments are monthly, so your units must be monthly. N is 30 years times 12 months, which is 360 periods. And I is the 6% annual rate divided by 12, which is 0.5% per month, or 0.005. Using the wrong units won't just give you a small error, it will give you a completely meaningless number. Second, incorrect interest rate input. Remember, the formula needs the decimal form of the rate. Typing in 7 for 7% instead of 0.07 will give you an answer that is wildly off. Finally, calculator errors, especially with that negative exponent. Always double-check your inputs. These seemingly small details are the hallmarks of a precise and reliable financial analyst.
So as we wrap up our discussion, I want to bring our focus back to the bigger picture. Why do we spend all this time dissecting just one formula? Because this is so much more than an academic exercise. This is a foundational skill for any career in management, finance, or entrepreneurship.
This quote really summarizes the core function of what we're doing. A financial manager's main job is to make decisions that create value for the firm. Well, this formula provides the mechanism to actually measure that value. By translating all future outcomes into the common denominator of present-day dollars, we can make objective comparisons and put capital toward the most promising opportunities. It helps us navigate the complexities of an uncertain future with rational analysis.
So let this be your key takeaway. In business, you're going to be flooded with promises, proposals, and projections. This formula is your tool for cutting through all the stories and getting to the objective financial truth. It transforms a subjective promise about future performance into an objective, comparable, present-day value. It empowers you to move beyond just a gut feeling and make decisions that are grounded in rigorous, data-driven analysis.
I'm going to leave you with one final challenge. Look beyond the corporate examples we've talked about today and think about how this tool applies to your own life. When you're looking at a car loan, don't just look at the monthly payment. Calculate the present value of those payments to understand the true cost of the financing. When you're comparing job offers, don't just look at the salary, discount any promised future bonuses back to today so you can make a true apples-to-apples comparison. You have now acquired a powerful lens through which to view financial decisions. My advice is to use it, not just in your careers, but in your lives. Thank you.